Okay, so can you see the distance between the microscope and the sample? Maybe we can call this distance d. Well, this is d and this is d also. So what we can see here is that the wavelength of microwave maybe is about 3 cm, maybe so long, and maybe the wavelength of visual light is just 300 nanometer. Well, if we put d here, it can be much shorter than the wavelength, right? But if we put d here, it will be much bigger than the wavelength of the light, right? So, to a conclusion, we see that here, if we use microwave microscope, this distance is near field. But compared to the visual light, this distance is far field to some degree. So what is the near field? It's a relevant definition. It's a relevant concept. The near field can be defined as the observation distance is much smaller than the wavelength. So this calls near field. And normally, near field in microwave microscope is about 0.1 millimeter or less than that. So let's make a conclusion. What is near field scanning microwave microscope? Later I will call it NSMM. It's a kind of microscope, but it's use microwave to take place of the light, and is scan the samples point by point, and is in very close distance. This is what is NSM. Does that make sense? Okay. Then let's make some explanation about permittivity and loss. So here I have to show you the equation. This equation is that permittivity, we call it epsilon, equals to this and this. This is the real part. Do you know real part? And this is an imaginary part. It's a complex figure. Do you know complex figure? Such as maybe we can say 3 plus 1i. Yeah, but in engineer we call this, we use j to take the place of i. So this is called a complex number, and this is the real part, and this is the imaginary part. Sorry, I don't know how to spell it. Imaginary part. So permittivity is a complex number, and this is the real part, and this is the imaginary part. Well, the real part of the permittivity is a property of a material, and the imaginary part of the permittivity is a representation of laws. So we can use the imaginary part to evaluate the laws, but maybe the real part is much more complicated till now. So let's make a little bit. Let's give you an example about what real parts means here. Maybe do you know antenna? Yeah, antenna. This is antenna, and maybe there is another antenna inside your iPhone. Well, the gain is a property of antenna which can evaluate is that antenna works well or works worse or works better, and this is a equation about the real part of the permittivity. So what the real part of permittivity can do is to maybe in this situation it can evaluate antenna. So maybe this concept is quite a bit abstract, but it's useful in engineering. So let's make a conclusion about what the permittivity. here we want to measure the real part and the imaginary part of the permittivity. And when we measure the imaginary part of the permittivity, we also measure the loss of the material. So here is what is permittivity, and here is what this article wants to do, is to measure the permittivity, both the real part and the imaginary part. And here we finish our definition explanation. So are you clear about that? Then I will give a brief introduction of the previous studies in this article. Well, in this article, the authors tell us about maybe the previous study can be divided into three things. The first thing is about some researchers measure the permittivity and the loss without an SMM. Well, the author told us the most problem of this research is that it cannot measure it in nanoscale. As we know that the permittivity and the loss can be changed by the frequency or by the scale. Maybe in nanoscale, the permittivity is higher than in millimeter scale. So it is important to measure the permittivity and the loss in nanoscale by NSM. I just mentioned that the near field is very close and it can observe in nanoscale. So that is why we need an NSMM. And then the author told us something about how to use NSMM to measure the permittivity. Well, there are two tabs. The first tab is to measure the complex reflection coefficients directly. What this means? This means that maybe you can look at this picture. This is an NSMM. Well, a light goes through from the coupler, and then there is a reflection to another coupler, and maybe we can see the receiver. Maybe we can see the amount of the microwave here is as a receiver, and here the amount of the microwave generated here as a transmitter. And this can be called a CRC. That is a kind of explanation of the coefficient. So what the researcher want to measure here is this. So this is the first step of the measurement. But the main problem of this problems is that there may be some other things that affect the result. As the author said, that it's a string capacitance associated with the AFM. Cantilever are difficult to compensate for. That means that there may be some other things I will show you later called cantilever will affect the result. That is the main problem of type 1. And type 2 is to measure the resonance frequency and Q effect. So here I want to make another explanation of it. What is the resonance frequency and Q effect? Well, let's look at this picture again. Well, what is the resonance frequency is that the microwave generated here is not a single microwave. It's a microwave with all kinds of different frequency. Maybe do you know frequency? Maybe the X label is time, and the Y label is dB. That is how big it is. And maybe the same time there will be a lot of signal generated, a lot of microwave generated. But when we look at this, it can be consist of a lot of frequency. Maybe we can draw another picture. this is at a frequency, and this is also dB. And maybe this is 1 gigahertz, and this is 3 gigahertz, and we can see maybe there are lots of different microwave go through from here. And what we can see that here is a peak. This peak value represents to an x-label point. This point we call resonant frequency. Maybe this is 1.3 gigahertz. So the resonant frequency here is 1.3 gigahertz. So the authors try to use this method, top 2, try to use this method to measure the permittivity. And the Q factor, Q means quality, is another measurement, is another kind of measurement, but related to resonant frequency, but it's quite complicatable. So I suppose that the explanation of resonant frequency is enough here. Well, here is 2 tabs about how to measure the permittivity by NSMM. And then how about the loss measurement? Well, the tab 2 measure the resonant frequency, and Q factor can measure the material whose loss is quite low. But the problem is that tab 2 can only measure the low loss materials, but cannot measure the high loss materials. So till now, what conclusion can we make here is that the author want to use tab 2 to measure the permittivity, and absolutely is an available way to measure permittivity. And the author want to also use the tab 2 to measure the loss of the material. But the problem of the author want to solve here is that he want to measure not only the low loss but also the high loss of the materials. So the author want to do first is to verify the tab 2 in measuring the permittivity. Then he want to make up some new method to measure the high loss of the material. So here's about the previous study. Does that make sense? So there are 3 parts in this study. The first is the system of the measurement. The authors taught us something about the equipment, and then is a series of the measurement, and last is the result and the analysis of the experiment. First, let's take a look about the system of measurement. When I looked this first time, I also think it's quite complicated. But maybe we can just look at the middle one. Here is an NSMM, and these 2 parts doing the job of scanning. Here he can adjust the high or low of the NSMM. And here is can do the scanning by move the specimen, by move the sample, and some other things like the piezo controller or this chamber or the table is an assistant. It works as an assistant. But the main point of this system is that there is the NSMM, and there is stages, and there is another stages. So this is a measurement system.
Okay, 5 more minutes.
Okay. And then the series of the measurements can be concluded in permittivity measurement by NSMM, which published in 2004, and another is the theory of complex frequency. Well, here is the result. Well, the first result is about the permittivity measurement. The authors used the equation published in 2004, and this equation is an empirical equation. This equation comes from the calibration. And here is a measured line, and here is a fitted line. And what authors want to show us is that when he changed the gap, what the gap is the distance between the microwave and the sample, he found that is different between the fitted line and the measured line. So the only part of the same is that the first 10 points. So the authors give us a conclusion that if we want to use this equation to measure permittivity, we can only use the gap between the microwave and the sample, which is lower than 10 millimeter. So here's the conclusion 1. And the conclusion 2 is that the authors use this theory we call complex frequency to measure the high loss of the materials, and absolutely he successed. Well, the last things I want to say is about the strengths and weakness and to weakness. First, about the strengths. Absolutely, this picture is quite complicated, but it gives us some new ideas about how to make our measurements more accurate. He used a chamber, a table, and piezo controller. So this gives me a lot of ideas to how to improve my experiments later. But what I want to emphasize is a weakness. I just said that there is a difference between the measured line and the fitted line. But why? I suppose this happened in the system. Well, you see that what the author tried to do is to adjust the NSMM by this stage. But what it will happen then? That there are a lot of lines to link the NSMM to maybe VNA analyzer. But when we move to this stage, the line will, the cable will move, and then there will be a systematically error happen. This move will affect on the result of the analyzer. So this maybe can cause this kind of difference. This is my guess. So the problem here is that the author shouldn't move this stage. Maybe they can use another way to adjust. Maybe he can put this stage here to move the specimen rather than the NSMM. So this is the first thing I think is not very good. And the second is that the author didn't give us many details about the empirical equation and the complex frequency. He didn't give us so much, enough information about that. So as a reader, I cannot justify whether his theory and his results is right or wrong. So this is as of the writer lack of explanation in service. Thank you. Any questions?
What is the most significant contribution of this article?
He measured the high loss of the material.
And nobody had done that before?
Yeah.
When was this field first studied?
In about 1960.
1960, okay.
Yeah.
So has progress been slow or fast over the years? Is it surprising that this has happened only now?
Yeah.
Yeah, it took a long time.
Yeah.
Yeah. So that's why it's so important.
Yeah.
Yeah. So what are the implications of this?
It can do a lot of applications, such as it can use
it has a lot of implications.
Yes, maybe you can use it to detect the body, to take the place of X-ray, and it can also do a flow detection, maybe in a current bore or flow, or airplane, and it can also measure the permittivity and or the conductivity like the authors did, and which can be useful in the evaluation in maybe some other fields like antennas or radar.
So that's what it's useful for?
Yeah.
I don't know what the effect of the move the low stage? You mean?
There will be there are a lot of cable which link the NSM to another analyzer.
You mean the equipment has lots
So-
of lines?
Yeah, there's a lot of cables.
Yeah.
So if we move this stage, it will be higher or maybe lower,
Yeah.
and then the cable will be moved, will be effect. Maybe
Yeah.
the signal will be effect, and the analyzer will be effect, and the result will be effect. So that is the logic.
But the higher also have some cables. If you move the high,
Example.
yeah,
But if we move the example, it will do nothing about the NSM.
really?
So the most of the cables are linked the NSM and the analyzer, but the specimen or the example is separated from the system.
So why we have to move the Z stage? We just
To do
Stick-
scanning.
okay.
Yeah.
So when you're scanning, so it will move.
Yeah.
Okay.
We have to move because
Narrow
this
the
is scanning. Sorry?
To narrow the gap of the.
Yeah.
Do you have a question, Bruce? Nope. All right, shall we leave it there then? Thank you very much.
Thank you.